All right. Good morning, everyone. Good morning, everyone. Good morning, everyone. All right. We're going to touch on two topics today. We are in block one. HL1. All right. I'm going to teach you guys another particularly useful trick when dealing with polynomials, finding roots, finding factors, stuff like that. Okay. And let me get my notes. All right. All right. This is a really useful tool, and in fact, it can really kind of cut through a lot of clutter. Um, all right, say you have a polynomial. For example, 2x squared minus x minus 45. All right. Now, you can, yes, you can stuff a rabbit. You're going to wind up with, 9 and 10. Pull out that rabbit, you're going to have 9, 2, and 5 in there, and you're going to have all sorts of stuff going on. But if you already know one of its factors, and I'm dealing with a small polynomial right now, but you can apply this to larger polynomials too. But if you already know that x minus 5 is a factor, what would you do? Yeah, you could do synthetic division or long division, whatever your personal preference is. But there's also another really cool way to find it. And especially useful when you're dealing with big polynomials that, you'd have to do lots of, long division for, or even a lengthy synthetic division. But it's applicable and useful in lots of ways. If this thing factors into x minus 5 and something else, right? Something else, whatever it is. We don't know, we don't care yet, but we'll find it. Then what we can do is say, all right, I don't know what A and B are right now, but let's just see if we take this thing a little bit further. And we say, we multiply it out. ax squared plus bx minus 5ax minus 5b. All right? I know, it's weird, because I'm kind of like saying, I'm introducing two unknown variables and throwing them into the mix and making something that looks really weird and goofy. But it's got a really neat application. Watch. All right. So all I've really kind of done is, combine my terms and, pulled out that GCD. So I'm kind of looking at a polynomial now, again, that is in the same style of normal standard form that we're used to when we think about a polynomial. But let's remind ourselves, and I'm going to give myself a little bit more room here, that is equal to this. These two polynomials are equal to one another, right? Now, if I look at this term by term, I've got a quadratic term. I've got a x squared. I've got a coefficient of -1 in front of my linear term. And my coefficient, sorry, my constant is a -45. Well, I've also got a quadratic term. Oh, sorry, a quadratic coefficient, a linear coefficient, and a constant. If this thing really is a factor, whatever ax plus b is, whatever this is, that means that this and that must be the same thing. Oh, you're here.
Yeah, my car runs.
No problem. You didn't miss much, except the quiz.
It wasn't bad.
It's just 2 questions. You'll take it later. That's fine. Okay, so we have this polynomial, and we know one of its divisors, and we can say that it must be broken into that factor and this other factor, which we don't know. And just recapping for you, expand it all out and group all of my terms, and now we can relate the coefficients to each other. The coefficient in front of the quadratic term must be the same as the coefficient in front of the other quadratic term. And the same thing is true for a and b. I mean, for the other coefficients. So now what we really have is saying we have a system. A equals 2. And we can also say, and we can relate these, and we can relate those. We don't really have to fool with the middle term because we can just get a and b from the first and last pieces, but we can say that negative 5b must equal 9. So as soon as you find one factor, you can find the other factors. And now we can say that 2x plus 9 is the other factor. So there are lots of different ways of finding possible roots of quadratics and other higher order polynomials. Let's try this again, this time with something with a little bit more gore on it, a little bit more fangs and claws, and see what we can use with it. Because it doesn't just apply to simple quadratics, it applies to all polynomials. All right. Actually, before we even go there, let's just have you do another one by yourself. Oh. As soon as we found one factor, we can use this technique to find the other factor, rather than doing division. You don't have to do long division anymore. That's really what this is getting at. Long division now kind of, it's a tool, but it's not the only tool. So, oh yeah, it's a lot faster and easier than long division. Oh, absolutely. Let's try this one. Yeah, it's nice to have a new tool in your toolbox. Okay, so we have, whoops. Yeah. All right, okay, all right. So we have this polynomial, and we know it is, one of its factors is 3x minus 1. So that's saying to me that it must be some. Now, we know that the other term must be a linear term, an ax plus b, because the highest order of the original polynomial is 2. Okay, if this was a cube, if this was 6x cubed right here, then we'd have to apply something else over on this other side. Okay, but remember, the very first multiplication, when written in standard form, has to produce that order of polynomial, So if that was a fourth, and you knew one of these, this would have to be x to the third in order to make it to work, It has to have that same exponent. And we'll do some higher order ones in a little bit. But try this one on your own and see if you can find out what a and b are. So multiply it out, collect your terms, and relate your coefficients to each other. We'll do one together. Are these all under control? Okay, so yeah, once you've foiled the whole thing out and you've collected your terms, that's saying to me that the 6 and the 3a must be equal. So 3a equals 6, a equals 2. And that also says that the 5 must be equal to negative b. So b equals negative 5. And now you can write this whole polynomial out in a little bit more generalized form. You can say, actually, so a heck of a lot easier than long division or even synthetic division, especially with a quadratic. All right, so let's take it another level up. Or would you like one that's a little more challenging of this? Good, let's see if you can do a challenging one. We'll get there. So find the value of k, and then find the other factor. Just work it out. See where it takes you. Dive into it. Jump off the diving board, and then look and see if there's water in the pool. Did you find it? Yeah. So what do you mean? Say it again. Yeah, well, you see, k is just a constant. So, yeah, whatever your last term would be equal to it. All right, so let's try it. Oh, all right, all right, all right. All right, so I think everybody got there, right? So I know that a is equal to k. I also know that b is equal to k squared. Those are for my first and last coefficients, right? And to get, you see now I've got two equations and three unknowns. So I need one more equation. And I get that by looking at the middle term. So I know that b plus a equals 2. And in fact, you could probably guess what it is, what they are, right? But even if you didn't, you could plug them right in. Now you've got a system of 3 equations, 3 unknowns. You can substitute and solve. And now you've got k squared plus k equals 2. So we have 2 possible values for k. So and now we should go in and confirm our results. Okay. First, we'll let everyone copy all that down. That's the kind of thing I would expect to see somewhere down the road. What? I didn't hear you. What?
It's a one-time situation thing that it's got lucky. You know that what function of x plus 1 makes it 2x in the middle? The only thing I can do that was the same thing. I mean, that was lucky.
Yeah, unless you had some sort of imaginary number in there, perhaps that could mess with you, and things like 2, right? Because 2 squared is equal to 2 times 2. All right. And we see that actually with -2 being an answer. So 1 and 2 are the only ones that would play. And then you've got positive and negative applications of both. So now we can go back in and see what happens. So now we can go, let's do the -2 case. We get -2x squared plus 2x plus 4, was it? Or was it minus k? It was plus. Okay. Plus 4 is equal to, now again we have x plus 1 and ax plus b. And now we can find those factors. You can find ax plus b for this case. And in fact, actually, you can pull out a coefficient, right? You can pull out a constant. You got a GCD in there, yeah? But you might even want to leave the GCD in just so that it would be left inside the ax plus b. But in either case, you'll find it. You just have to keep good accounting and keep that -2 out in front. But let's go ahead and blow it up. And there's your A and your B. Bless you. It was the quietest sneeze I've ever heard. Okay. And of course, for the k equals 1 case, now I've got x squared plus 2x plus 1 equals, and I'm just going to go ahead and jump up to this one, or rather to this one. And now b equals 1, and so does a. So this is a useful tool for solving some problems, okay? Because you can create equations using the 3 coefficients or more coefficients that you have. So don't be afraid of one like this, okay? And actually, I'll give you one that you can put in your notes and try later on, okay? So we're not going to do this one, but you can do this one on your own later on. Okay, so for your own edification later on down the road, okay? Okay, let's try one with some real fangs and teeth. Let's do a 5th order polynomial. Forget about the cubes and the quad and the quartics. We're just going to jump right to quintics. So, all right. Okay. So if you had to do that wacky, crazy polynomial division, the first thing, what is one thing you can immediately say? Oh yes, you definitely have a GCF. But what we also can say is that this thing divided by that thing has to produce a polynomial, another polynomial, right? So I can say, I mean, like, what am I really saying? I've got this gigantic polynomial, let's call it p, and it's divisible by some other polynomial, we'll call that phi, and it's equal to another polynomial theta, okay? Some Greek letters in there. So what that's also kind of, you can write it like this in a sense. Right? Well, they're just polynomials. So that means that the original guy is equal to theta times phi. All right. So what I'm getting at here is that I can rewrite the initial equation as this. Actually, times some other wacky, crazy polynomial. And that's what we're going to find. We're going to find that crazy, wacky polynomial that it's equal to. All right. But before we even go there, as you said, we've got a GCD. I'm just going to divide that out right now. Times somebody else, somebody big. All right, now what is that big evil polynomial actually really supposed to be? Well, actually, I'll do it on another line. So, m times something gives me m to the fifth, right? So what should this exponent be? To the fourth. And you're going to get some crazy system of equations. So, am to the fifth plus bm to the fourth plus cm to the third plus dm squared plus em, right? Plus I'm doing all of those. And that gives me this piece. And now I've got one more to do. Let's just see it. Now I do the next one, minus am to the fourth minus bm to the third minus cm squared minus dm minus e is equal to my original polynomial. Yeah, a lot in there. And now we can combine like terms. And now we can correlate our coefficients, or we can say that, well, looking back at the original polynomial, I can immediately say what? Yeah, a would have to be 1, right? And what also do we get for free? And the last one, e is equal to negative 3. Okay. And we can create other series of equations as well. We can say from the second coefficient that b minus a is equal to negative 8. But hey, we already know what a is, right? We can plug a back in, get b. And then we can plug b into the next one and get c, and go down the road. You see? Oh, wait, sorry. I skipped one. Yeah, it should be minus e, shouldn't it? Good catch. So now I know that that's true. E is equal to 3. Thank you. Go ahead and find my C, D, and all you really need now are C and D. So go ahead and find those two. So we all get it? Is that what you guys got? 0 and 3. So now we can do this. We can go back to the original. And say that this is equal to, was it x plus 1? X minus 1. Yes. Hmm? Where are you? Ooh, sneaky. They snuck one under me. There we go. D should be 0. So let's go back. Nice catch. Oh, you should have said. I didn't understand. Yeah. Yeah. The other piece? Because what you're saying is that I have polynomial times constant equals polynomial times constant. So I just cancel out the constants. Because if you think about it, I'm saying, and let me finish writing this and then I'll show you. This would be, what do we have? X to the fourth minus 7x to the third plus no x squareds plus no x's minus plus 3. Right?
So would there be no, but I mean, if we have extra
Hmm?
thing we don't need.
Like what? Oh, like a missing term? I'm confused too. I don't know what you're asking.
I'm asking you that.
And we can actually check this by multiplying it out. I didn't say x. I shouldn't say x. They're m's, aren't they? And let's confirm it. Which was the original function. See how that works? A little bit. Shaky ground. Oh, the GCD. Okay. It's a lot in there. Okay. So let's do a simple one. All right, okay, so if I were to factor this right away, right, I can come up with, oh, actually, let's just make it even simpler. So this by itself, if I did this, I could say, right, whoa, you got that slide? Are we we cool? We're good? Now, I just multiply it in. So in a sense, you can see that I only have to pull it out of one. See, because otherwise I'd be pulling a 2 out of the first one and a 2 out of the second one, which would be a 4, which is not the same on the other side. Okay. Now, so equating coefficients is a useful tool. We can definitely speed up things with it, especially, particularly evil ones, which will be coming at you soon. Now, what if you had no idea whatsoever what any of the factors were? You just were thrown a polynomial and said factor it. It was some evil, horrible, gruesome thing, and you didn't have a graphing calculator. You didn't know what to do. All right, let's try one of those. All right. Let's see if I can get a good one for you. Ooh. Where's that page? Where's my page? Not equating. I lost my page. All right. Equating coefficients. Okay. And you were supposed to factor that. Yeah. You could stuff a rabbit. It's one way to play it. But you could also find what the possible zeros are. Because remember, if you can tell me where a 0 is, you can tell me what a factor is. Because remember, when you look at that graph and you see that kind of a graph, you're looking for those points and say, like, if this was, 1/2, you would say that x equals 1/2 is a root, so therefore 2x equals 1 and 2x minus 1 is a factor, right? So if you find your roots, you can find your factors, right? So what I'm really looking for is, if I don't have a graph, is saying, okay, what gives me a 0? What number, when plugged into that beast, gives me a possible 0? Well, here's how you do it. You look at the same idea behind stuffing the rabbit, okay? But the idea there is, because the idea was that there's some relationship between the first coefficient, the last coefficient, and the zeros. Because when we stuffed rabbits, we were fooling with those two coefficients. And those two coefficients gave us the factors. They are very much intrinsically related. And actually, when we found, what was it, the product of all of the roots, it dealt with those two coefficients as well, right? So, -10/6. Okay? Let's simplify that. Now, the possible roots are the positive and negative factors of this fraction. So plus or minus 5/3, plus or minus 1/3, plus or minus 5, plus or minus 1. Those are the only ones that we really have to check. And if we take those 8 possible numbers and plug them into the original function, any one of them that gives me a 0 must be a root. Yes. Because 3, the positive and negative, the positive and negative factors of 5, and the positive and negative factors of 3. And since 1 is a factor of 3, so this is basically saying 5 over 1, right? Okay. So do you see how we found all 4 of those numbers? The factors of 5 are 1 and 5. The factors of 3 are 1 and 3. So it's all the possible combinations of 1 and 5 and 1 and 3. Okay? That make sense? Who has no idea what I just said? What? 1 second. What? Because 3 is in the denominator. I'm just looking at the 5 and the 3 where they are, that fraction, 5 over 3, right? And I'm looking at those possible values. I'm not swapping, I'm not changing them upside down. I'm not taking reciprocals or any of that stuff. I'm just saying, in their current location, what are the possible factors and the possible factors? Yeah, well, in a sense, the factors of 5 are plus or minus 5 and plus or minus 1, right? Those are the possible combinations. And if we went down the road on there and looked at all of the possible combinations, we would have 5, 1, 1/3, and 1, and 5/3. See? You see where those values come from? So before we go anywhere on this, okay. Find me all of the possible values that you could get. List the possible choices that you could use for that one. And it's not going to change the work you're doing, but I'm going to make it so that it'll actually work. We'll actually use this as an example. It's simple enough. And that would mean that this has to be a negative. Doesn't change what you do. You should still get the same positive or negative values to play with, right? I just changed it so we could actually use it. So we have the positive and negative values of 5 and 1, and the positive and negative values of 2 and 1. No, I'm just throwing out all the possible choices just so that you can visually see them all. So my choices are plus or minus 5, plus or minus 1. That's if I chose 1 in my denominator, right? The one, it's this guy and this guy. Give me those. And this guy and this guy gives me that one. Okay? And the other choices are plus or minus 1/2. And that's it. And yeah, that's it. And 5/2. 5 over 1, 1 over 1, 1 over 2, and 5 over 2. Okay, those are the only 4 that we really have to check. So now what we're going to do is plug in some of these values, and if we land on a 0, we stop. So, what's the easiest one to pick? 1. I'll call this P of x. Let's do P of 1. 2 minus 3 minus 5. Does that fly? Does that equal 0? No, that does not equal 0. That one's out. How about P of negative 1? Right? Does that fly? It does, doesn't it? So now immediately I have a 0, which means I have a factor. And then all I have to do is go in there and find my other factor. So I can say that P equals negative 1 is a root. So P plus 1 is a factor. So what did we say? 2x squared minus 3x minus 5 is equal to, x's or p's?
X.
X. All these funky variables. Now use equating coefficients. What does A and B have to be? Done. That's it. This is a really nice way to find the first factor. If you find the first factor, then you can simplify it to smaller factors. All right. It almost is, right? It's almost magic. So don't sit there and try and divide the thing. What are you going to do? Plug in what? Plug in 2. See if it flies. What, the other example? No. Because if x minus 2 is a factor, then x equals 2 is a root. Yes, so if it's a root and I plugged it in, I'd get a 0. All right, so is it? Good. Find the other factor. You see, it's really cool when you can equate coefficients because you can just bam, you do it in 1 second. Yeah. What am I A and B? What does A have to be? 3. And what does B have to be? Positive or negative 4? Yeah. Is it positive or is it negative? Yeah, it's negative because whatever it is, negative 2 times something gives me 8. Right? Yeah. Okay. But I'm messing myself up already. Oh, wrong one.
Sorry.
That's okay.
I was using two people instead of the keys. Thank you.
No problem. So the 3 must equate to the A, and the 8 must equate to negative 2B. So that's how I can find him. It's a heck of a lot nicer than trying to do division once you know what you're doing, especially for a quadratic. It becomes a quick and simple little nothing. Yeah. Well, I mean, I could have given you, instead of x minus 2, I could have said x minus 3. And that wouldn't have worked, wouldn't it? Well, no. I said, is it a factor? Is this a factor? Oh. And yeah, that's cool. And so now we know that, A must equal 3, and B must equal negative 4. And what's nice is that we can look and say, all right, what were my roots? Well, my roots now, which we know are 2, and the other root is 4/3. Those are the 2 possible roots when we set those equal to 0. And if we go back up to what we knew about these 2 exponents, these 2 coefficients, 4/3 would be in the list of possible factors of this guy, right? Because the possible factors for this guy to use would have been plus or minus factors of 8 and plus or minus factors of 3. And that's a lot to check, but they exist. Those are the ones to play with. And of course, the obvious ones of 1, -1, 2, -2, those are quick and easy, you know, and those are great to check. But when you're looking at some goofy polynomial and you have no idea where to begin, it's a good place to start, especially when you're looking at some polynomial that looks like this. You know, If you've got some crazy polynomial that starts with some gigantic coefficient, some gigantic exponent in the beginning, missing terms, all sorts of evil stuff in there, and 1, you can say, all right, let's just check positive and negative 1. And if we got those under control, we can find another set. And then we can try and find again and again and again and again and again. Okay. So, let's see if we can get another one. Ooh. Yes, it is. Oh yeah, yeah. I'm totally okay with, being the harbinger of doom. It's fine. Okay. And then factorize completely. That was a quick period. Bummer. Sure. Yeah. All right. This episode of the Ronco Show has been brought to you by the remainder theorem and the factor theorem.